Suppose C and H are subgroups of a group G. So C is cyclic and H normalizes C. That is, H is a subset of the normalizer of C. And H is equal to its commutator subgroup. Then show H centralizes C. That is, H belongs to the center of C. Since C is cyclic, C is equal to the group generated by little c for some C in big C. Since H belongs to the normalizer of C, this means for all H in H, H big C, H inverse, is equal to big C. i.e., for all H in H and C prime in C, H C prime H inverse is equal to C to the power k for some k, since C is generated by little c. In particular, H C H inverse is equal to Ck for some k. Now naturally, as this is conjugation, we consider phi from H to the automorphism group of C. Defined by phi of H evaluated at C is equal to H C H inverse. Simply conjugation. Then clearly phi is a group homomorphism. Since H is equal to its commutator subgroup, and the commutator subgroup of H is normal in H, by previous. It makes sense to take H mod its commutator. But since they are equal, this is isomorphic to your favorite, the trivial subgroup. And by the first isomorphism theorem, we have H mod the commutator of H, that is the commutator subgroup of H, is isomorphic to phi of H. The image by this homomorphism phi we defined here. So phi of H is isomorphic to the trivial group. Therefore, phi of H is equal to, well, what? Things living in the automorphism group of C are isomorphisms from C to C. The trivial isomorphism from C to C is simply the identity map on C. But then, since this is the identity map, phi of H evaluated at C is equal to H inverse that is phi of H evaluated at C must simply return C. So K is equal to 1. More importantly, this means that HC is equal to CH, which shows in general that any element of H belongs to the center of C.